So far, we have discussed how large deformation makes a model response nonlinear from a physics standpoint. But linear or nonlinear behavior is a mathematical interpretation of a physical system. So, in this lesson, we will learn how the large deformation is treated mathematically. While doing so, we will also investigate what mathematical approximations do we make when we assume a system to be linear. This knowledge is important as the analyst must be aware of the simplifications that they make, so they are aware of the consequences. Now, let's learn the difference between the large and small deformation. Of course, big or small, physically there's no difference, but mathematically we can simplify some class of models. Before we jump into it, let's take a look at a new term called as the deformation gradient. Let's consider a random shaped solid and let's focus on a point on it. When you apply some load on this object, it deforms and displaces, and the point now assumes a new position in space. We can track the change in positions of this point by inspecting its vector in space. In the undeformed state, it is in a vector space capital X, and after deforming, it moved to a new location small x. So by definition, the displacement of this point is nothing but the difference of the initial vector from the final vector. If you observe this relation, you realize that it does not tell you whether the body is simply translated to the new position or if it deformed on its way there. It's important to be able to identify this, as the stresses will be developed in the object only when there is a deformation in it. So we define a new term called as the deformation gradient. The deformation gradient is the derivative of the vector in deformed configuration with respect to the undeformed configuration. This definition alone may not convey the physical significance of this term, so let's look at this simple example. Here, the object is simply drifting from one place to another. This is simple rigid body motion and no portion of the body is deforming. This means that the vector x is just a linear function of the capital X. If you compute the deformation gradient for this body, it reduces to an identity tensor. If this was not a rigid body motion, and instead there are portions of the body that are stretching, in that case, the vector small x is no longer a linear function of capital X, which means that the deformation gradient is not an identity tensor. So clearly, we can distinguish between rigid body motion and deformation based on the deformation gradient. For this reason, deformation gradient will be the fundamental term that we use in calculating different measures of strains. Now, coming back to the discussion on large strain. Let's start by looking at a measure of strain called as the Lagrange strain. There are other measures of strain that are commonly used, but we'll focus on just the Lagrange strain for now. The Lagrange strain is defined by this relation. While this advanced math may seem a little intimidating, it is enough to know that the physical significance of this term is that it quantifies the change in length of a unit material. Since f is written as a function of displacement field, we'll substitute that relation here and expand the definition of large strain. Once we do that, this is what the individual components of the Lagrange strain tensor look like. If you observe carefully, each component of the strain tensor has a linear and a quadratic component. Now, these relations can be used to distinguish between the large and small deformations. When the deformations are very small, the derivatives of the displacements will be small, and when we square these terms, they get even smaller to an extent where they are negligible. If we ignore these terms, we can reduce the strain tensor to just the linear terms, so they can take a linear form. Comparing these two strains, one can clearly see the fundamental difference between the strain tensors using small and the large deformations formulation. We ignore the higher order terms in case of small deformation, which is valid only when the deformations are small. By doing this, the equations will remain linear, and we can use linear solvers to analyze such systems, which are much less expensive compared to their nonlinear counterparts. But note that as the deformations increase, these terms get bigger and may no longer be neglected. This is the main difference between the small and large deformations. If the deformations are small, the quadratic terms are negligible. But once they start increasing, the errors due to simplification would start growing quadratically.